yet again, and today we're going to be talking about reaction kinetics. So hopefully you remember a little bit from your chemistry and equilibrium constants and engineering 45 and probably chemistry 24, material science, all those good classes because they always come back. And I'll tell you a fun story about an interview I had at Intel, and I was really, really glad that I remembered some of these kind of more elementary, not elementary equations, but some basic equations that you might forget and will be useful for an interview. But anyways, so we've talked a lot about extent of reaction. We know our Carruthers equation, which is just right above here. So we've talked about extent of reaction, P, how that changes as a function of time. It also changes as a function of, excuse me, erase this. P will change as a function of time. It also varies as a function of temperature, lots of other kind of different parameters here. But we need to understand the kinetics that control this process. So we need to look at equilibrium constants, KEQ. So hopefully you remember kind of what was going on there. So we're going to start very, very general, look at a generic step polymerization reaction and route. And basically we're going to look at A and B functional groups react to form a new linkage between the two monomers, C, and then there's this byproduct. So very similar to what we're building up slowly, and then we're going to kind of create this new reaction. So let's just say we have a reaction A plus B leads to, reverse as well, C amount of C group plus D amount of B group. That's it. So that's what we're working with here. So what is my K equilibrium constant for this expression? Well, we know it's the concentration raised to whatever the power on that prefactor is, C, concentration of products over concentration of reactants. That is our K equilibrium constant. So this is a really, really, really critical expression here. So again, all we're working with is we have kind of some structural unit here, a structural unit here. We have some functional group AA. Again, there could be two, usually we've kind of drew this previously. There could be BB, but just to kind of keep it simple, A is going to react with B here. We're going to form this new linkage C and some byproduct here. Again, this could be H2O, this could be HCl, it could be something else. We're going to see here. And this is the rate of the forward reaction. This is the rate of the backward reaction. And that is essentially your K equilibrium constant here. Again, it's not raised to the power because this is just a more general expression, but I like this expression here. So the reason I bring this up, I was actually asked in an interview in Intel to kind of write this K equilibrium constant of a generic reaction, and then there was lots of other questions that followed. But if I would have forgotten this, which is definitely easy to do because I'm not a chemist, I'm a material scientist, but luckily I was teaching a course where we were covering this, so that saved me. So remember this, it could show up on an interview at Intel. So this is your concentrations, this is your rate of your forward reaction rate. This is your, sorry, it's the forward reaction rate constant, K. This is the backward reaction rate constant, Kr. And then the rate would be that constant times those concentrations. So how are we going to use this K equilibrium value? Why is it useful? Again, we're always focused on how can we use these parameters, how can we use these expressions in order to control the properties of our, or design actually the properties of our materials. Well, one simple way that, or one of the key reasons is we want to be able to control the degree polymerization, and then thus, which scales with the molecular weight, because that's going to change a lot of our properties, the number average molecular weight. So if I want to control this, specifically if I want to increase it or decrease it, I need to understand, and if I want this reaction to proceed, again, this is controlled by that rate of extent of reaction, P and R. So we know that P depends on these K equilibrium value. So I want my K equilibrium, my rate constant, or my K equilibrium constant to be extremely, extremely, extremely high, 10 to the 4. Why do I want that high? Well, if I look at my expression here, if the concentration of my products is really, really, really large as compared to the concentration of my reactant, my reaction is proceeding forward. So again, if my K equilibrium is large, hopefully it's around 10 to the 4th, that means that there's more products being formed than reactants. Our reaction is moving forward rapidly. Again, we're producing our products, which is our high molecular weight polymer chains, hopefully, as long as we're sticking with the Carruthers equation. high reactant ratio, almost 1, and large extended reaction. Now, what happens? So we want that. This is the ideal situation. We want to create more products than reactants. But let's say that we're stuck with our chemistry. We can't kind of, sometimes you're stuck with your reactants A, B, and your products C and D. And there's nothing you could do. You have to react monomer A and monomer B. And let's say, for example, that due to your chemistry and due to your experimental conditions, your K equilibrium is about 1. So that's not a great situation to have, because that means that we're basically forming just, we're not forming reactants at large enough concentrations in order to kind of, again, get our polymer at high molecular weights in an appreciable amount of time. So we need to kind of do something in order to make our reaction proceed more and to kind of get more products. So just like we said, one option is changing our monomer and our A and B, our structural units. But let's say, for example, we can't. So that's not an option. One option that we have is to hopefully remember from chemistry, Le Chatelier's principle. So we could bias our reaction forward. So what we can do, going back to this K equilibrium equation, if KEQ, actually we'll write it over here, our K equilibrium, again, is just this concentration of products. Oops, excuse me. Undo that guy. Concentration of products over concentration of reactants. And this is just a fixed equation. So if this equals 1, and we cannot, change that, but this value has to be the same. So this concentration constant, this concentration constant, this concentration, this is what, we're going to produce this amount. One thing we could do to bias the equation is to remove, just basically remove the byproducts. So remove that D byproduct that's formed during this, again, this step growth polymerization route, this, condensation reaction, although we said we're not going to use that one. So if I remove this concentration, my K equilibrium still must be 1. So that's going to bias, and it's going to create more of our concentrations, or again, there's going to be a smaller amount. We can't remove all of the material here, but in order to kind of maintain this K equilibrium constant, if we remove this byproduct, it's going to create more. The C concentration has to increase in order to satisfy this expression. So that's one way that we could kind of move this reaction forward if we're stuck with this kind of lower reactivity K equilibrium constant. So that's one thing to kind of point out. So now it's time for chemistry. But before we get into kind of chemistry and creating our own polymers, we want to kind of talk about one of the most common chemistries and modes and methods and procedures of linking polymers together, which is via this nucleophilic acyl substitution. A lot of words. We're going to break it down step by step. So first, hopefully you remember, nucleophile is an electron-rich species. So nucleophile will typically have some negative charge. It's rich in electrons. It has lots of electrons, and it wants to react with an electron-poor species. So some species that probably has some partial charge. So X, some partial charge, and it wants to give up and donate that electron. So when you think about donating an electron, we're looking for materials that have electron-rich and that that have a low electronegativity. So we want to look, that would be our ideal nucleophile. Something that's partially negatively charged because it has an excess of electrons, that has low electronegativity because, again, we want to give up that electron and react with those kind of electron-poor sites. And ideally, your electrophile, which is an electron-poor species, we would want this to be also very electronegative, but we'll see that might not often be the case. So the electrophile is an electron-poor species. It is going to accept, and it's going to accept those pair of electrons. So electrophile, seek out these electron-rich sites. So this is a nice schematic of basically how nucleophilic acyl substitution works. So we have what's called, here's our nucleophile, which we kind of just drew here. This L is called a leaving group, right here, LG, but this is just L. You have our R, and this is just again, just an example or a schematic of some of the types of acyl groups that you'll deal with. So what happens here? Let's look at this structure. Let's draw it over here. I have my carbon, oxygen, leaving group, and I have my nucleophile. So my nucleophile is partially negative. Hopefully it has low electronegativity. Where is the electron? Again, my nucleophile is electron rich. It wants to react with something that's electron poor. What element here is electron poor? Well, look at this carbon, right? So we know that oxygen really electronegative. So it's going to pull away more of these electrons. So it's going to have that partial kind of negative charge here. L is your leaving group. We're going to see different leaving groups are going to kind of increase the reactivity of this nucleophilic acyl substitution route. But let's say that this is fairly electronegative too, so it's going to pull away electrons from here. So this will also have some little slightly negative charge forward. So here, this will have kind of this slightly positive charge, right? Electrons are being pulled here, electrons are being pulled from here, and now we have this kind of, again, our nucleophile, which is electron rich, wants to seek out an electrophile, which is this again, electron poor species, and it wants to react and donate an electron here. So the nucleophile is going to attack right here. So it's going to attack that bond, and it's actually going to break it, donate an electron, and transfer. So you can see here we go from this kind of trigonal planar configuration to a fully saturated carbon. So we go from this configuration here to C goes to R. This is just your fully saturated tetrahedral sp3 bonding configuration. So you have your nucleophile, leaving group, and now your oxygen has this negative charge here. So this is kind of an intermediate step. This is obviously not kind of stable. So what happens is that this does not like this configuration. This this is not a favorable configuration here. So the electron basically is donated, and again, so we have there's kind of an additional nucleophilic step here. So now this is kind of like our nucleophile. This is going to be our electron poor species. It's going to be transferred here, and the leaving group is going to be expelled as a byproduct here. So the leaving group is expelled, partially negative, and that's it. So it kicks out that leaving group, that hence the name leaving group. So what you end up with is, again, the name of this nucleophilic, the nucleophile substitutes in for your leaving group here. That's it. That's kind of what's going to happen through all our polymer chemistry that we're going to do in this class. Now, let's talk a little bit, or let's look at what makes a good leaving group. If we want this nucleophilic acyl substitution to proceed as well as possible, what would be a good candidate? What do we want? What attributes do we want for our leaving group? Well, the nucleophilic attack, nucleophiles and electron-rich species, it wants to react with an electron-poor species right here. So we need this carbon to be basically electron-poor as possible. So we know that O has to be there, but it's also very electronegative. What do we want for our leaving group to make this carbon even more electron-poor? We want that to be extremely electronegative. Very, very, very electronegative. We want chlorines, we want fluorines, we want all those elements in your periodic table that are really, really high electronegativities. So when we look on this table, which I really love this graph, very, very important, you're going to see lots of nice figures in this lecture. Not to toot my own horn. But if we look at this table of reactivity, so if we're reacting, if we're looking at these different leaving groups here, so COR here, here's a leaving group, here's our leaving group. We can see chlorine, very, very electronegative, highest reactivity, 10 to the 4. We want to react with these acids. We want that chloride to be our leaving group here. This is what we want to work with in these, if we're doing this nucleophilic acyl substitution to create our polymers. This is also very high. Once you get into the esters and just these really O's, they're electronegative, but they're not really, really electronegative. Obviously not as electronegative as chlorine. And then once you get to kind of your nitrogens, they get really, really low here. So once you cross kind of this threshold, you're going to have to do some tricks to make your action proceed forward. So you're going to have to remove byproducts here. Why? Because this value is too low. We want KEQs on the order of 100, 1,000, 10 to the 4. That's ideal here. Once your K equilibrium is around 1 or less, we need to do tricks. We need to make sure if we want to make a polymer with appreciable molecular mass, we have to kind of basically do something and intervene in our chemistry process. So that's where we come in. That's where that's why we're polymer scientists, engineers, chemists, and that's what we have to do in order to kind of make the materials that we need for any given specific application. So that is really quickly, nucleophilic acyl substitution. We'll talk more about it, but that's kind of the basics. Again, you don't need to know, this isn't a chemistry course, but you're going to see that this is going to come in hand when we finally, next time in the next video, we're going to finally make some polymers. So get ready for my really poorly drawn chemistry, but we'll work with this next time. So we'll finally get into polymers and making them. All right, thanks. Let me know if you have any questions, and have a good day, stay safe, and I'll see you next time. Thanks, bye.